So here's a problem. What's the greatest common factor of 2/5 and 3/7? It did give me a bit of a pause at first thought because we're so used to the greatest common factor being a concept related to natural numbers only that it takes a moment to decide what counts as a factor for a fraction. For a natural number, say 6, a factor is another natural number, say 2, that divides evenly into it, meaning gives an integer quotient. But if both the factor and the quotient are integers, the original number can't be a fraction like 2/5. To extend the definition of factors to fractions, we'd have to allow either the factors themselves or the quotients, or both, to be non-integers. Let's look at each of those choices. If we allow both to be fractions, then any fraction can be a factor of any other fraction. 2/5 divided by 103 over 47 is 94 over 115. A statement like 103 over 47 is a factor of 2/5 doesn't mean anything anymore. If we allow only the quotient to be fractions, then again, any natural number can be a factor to any fraction. 2/5 divided by 103 is 2 over 515. Again, a statement like 103 as a factor of 2/5 doesn't mean anything. So the only way for the concept of factors to still have some kind of meaningful distinction is to only allow the factors themselves to be fractions, i.e., even though they don't have to be integers anymore, they still have to divide evenly into the original number. Now we can take a look at the problem at the beginning, which can be translated into what's the biggest number that can divide evenly into both 2/5 and 3/7. Notice that in this extended definition of factors for fractions, there are a couple of differences with how things work in the realm of natural numbers. First is that factors don't come in pairs anymore. For natural numbers, say 2 is a factor of 6 because 6 divided by 2 is 3. Then 3, the quotient, is also a factor of 6. For fractions, 1/10 is a factor of 2/5 because 2/5 divided by 1/10 is 4. But 4, the quotient, does not divide evenly into 2/5. 2/5 divided by 4 is 1/10, not an integer. The second difference is that every number now has infinitely many factors. So it'd be impossible for us to list all factors and then find common ones. That's not a huge problem though, because the order we're using to list the factors here is from the largest to the smallest, which means the first common factor we find is the greatest we're looking for. There's the answer to our problem at the start. But we can dig a bit further on the concept of factors of fractions. For one, does the Euclidean algorithm still work? If you recall, the Euclidean algorithm is a method of finding the greatest common factor between two natural numbers that doesn't involve listing factors at all. All we need to do is to keep subtracting the numbers we have and replacing the larger number with the difference until we get 0. Like this. The answer there is the same answer we got earlier. So it suggests that the algorithm still works. I've always felt that the Euclidean algorithm is more about finding a relationship between any two quantities than anything based on the discrete definition of factors. After all, we can perform it with just two arbitrary pieces of paper strips without even knowing their measurements. There's also the question of whether this formula involving the greatest common factor and the lowest common multiple still works in fraction form. In natural numbers, this is true because of the inclusion-exclusion principle of the prime factors of the two numbers involved. Now in the extended definition, every fraction has infinitely many factors, and we don't have prime numbers anymore. Is that going to affect how the formula works? We know the greatest common factor from earlier, verified by the Euclidean algorithm as well. We can also find the least common multiple just by listing multiples of each of them. Let's check the formula. I wonder if this means we can reconstruct the Venn diagram used in the inclusion-exclusion principle. The greatest common factor goes in the middle, and the rest of the spaces can be filled with the multipliers we need to get back to each of the fractions. And there we have it. We get the same least common multiple we got before. Phew, math makes sense again. Now the question becomes how far we can extend this definition of factors. Can we also do this for irrational numbers, complex numbers, vectors in general? Let me know what you think in the comments below. And until next time, stay curious.